I have a third part of the compression unit where the methods technically are not compression methods, but they are useful in compression by, in a way, transforming the data into a more convenient form. We'll see basically two of these, and both turn out to be effective in their own quirky way. I'll comment more on that later. So to sum up the table from before, we've seen ways to exploit redundancy in various methods. If you have a character repeated many times, run length encoding captures that. If you have frequencies of the characters that are vastly different, some characters much more frequent than others, then Huffman's your guy to capture that redundancy. And if you have particularly long local repetitions, something like well, okay, don't want to go too deep into any specific cases, but some text that keeps repeating, like the Shining text would be one. It's always the same sentence, so it's never far to reach back to the last repetition. Then Lempel-Ziff methods work very well. If you apply these to all sorts of data that arises in application, it's sometimes super frustrating to see how blind they are to obvious redundancy, but obvious to you as a human. Some examples: if the repetitions are too far away, Lempel-Ziff has flushed the dictionary and forgotten everything, so then it wouldn't work. If you have, say, a text with lots of A's in the beginning, lots of C's at the end, then overall A's and C's may be equally likely, have the same frequency, and Huffman wouldn't be able to exploit that. But in the first half, you should have really used a shortcode for A, and in the second half, a shortcode for C. Huffman can't really do that. So it would be nice to have that more locally, but it seems to get complicated to figure out a good way to do that. And of course, run length encoding is so restricted that there's many ways how to make it not work by just breaking runs. And still, if you have some pairs alternating, it feels like it should be a run, but it doesn't work with run length encoding as we defined it. And that's where text transformations can sometimes help. They at least broaden the range of texts, or the range of data sets that compression methods can find redundancies in. They're similar to our compression methods in that they have a source code and a coded source text and a coded text, and you can go back and forth. You don't lose anything. But the goal for them is to not directly reduce space usage. That's why they're not called a compression method. They're just there to set the stage for one of the previous methods to pick up the redundancy that's there. And so they're used as part of a pipeline. I think this becomes much clearer with a concrete example. So let's see our first one. The first text transformation is called the move to front transformation. And it comes from something that some of you may have seen. It's often, so this is like a little digression. Forget compression for a minute. This is a lovely little data structure problem sometimes used to introduce competitive analysis and online algorithms and things like that. If you've never heard any of these, don't worry. You don't need that here. It's just for context, and make the connection if you have seen it. The goal there is to have a self-adjusting linked list. It's just a linked list as you have seen it in our implementations for stacks. And it's unordered. So if you search for something, you have to start reading from the beginning and walk your way through the list. Now, the question is, what order should you keep the elements in? In principle, because it's unordered, any order is fine. But here, the goal is to make use of the fact that maybe some elements are needed more often than others. Or maybe if an element was used now, maybe it's needed soon again. Things like that. And so as a very simplistic model, you can say, let's pretend we have to keep it in a linked list. But when you access an element, you've walked through that list anyways, so you may as well restructure it while you're going. And in general, you can pay more and go further and restructure more. That's the game in the self-adjusting linked list world. Now, if that sounds interesting, I'm happy to give you pointers where to read more. All we need for here is the following strategy that turns out to be a relatively good strategy for this problem. It's very simple. That's what it's written here. Whenever you access an element, you walk through the list until you find it, and then you rip it out there and put it at the beginning of the list. And intuitively, it's something like a least recently used ordering. Right? The item you've just touched becomes the first. The next item is the one that you used before that, and so on. So over time, you order the list in this order of least recently used. Most recently used? I think least recently used is the cache eviction strategy. You sort the items by when you used them last. Very at the front. Okay, I think you get the problem. And so over time, the list somewhat automatically learns which elements are used more often. What does all of that have to do with compression? So let's come back to text. The idea that people had was, let's apply that to our source alphabet. So we throw our source alphabet in a linked list, and we apply this move to front rule. Whenever we encode, when we find a single letter, we find it in the list. We represent it by the index in the list that it had, but then we move it to the front. That's pretty much what it does. So that's just saying what I described. You find a new letter in your string, in your source text. You search it in the list, starting from the beginning, and use the position as the code word. Then you move that element to the front and keep going. So the code words now are integers. You transform it from some arbitrary alphabet to the integer 0 up to sigma -1. Let's see. Maybe let's do that first. So just to see if the idea is clear enough. Again, this is not a question that's supposed to be tricky. Just making sure that my hand-wavy explanation without a concrete example was enough for you. So the way to read this, here's the front. You have these letters in the list. So there's, I don't know, shall we draw these lovely diagrams? There's X, and then pointer to the next element Y, pointer to the next element Z, and so on. All right, now we access A. What does the list look like when we're done? Let's wait for 30 people again. "13 to go." All right, the spelling, how exactly you format things, that screws up the display a bit, but other than that, I think most people got it. Shall we wait till 25? Is anyone still working in here? Looks like not many. All right, 25. So let's see. There's a big blob for A, X, Y, Z, B, C, and the usual. And that's the correct answer. So what you can do nicely here, okay, copy. Let's see if that works. This time it does. So we have that list before, and then after, what we do is we traverse, we walk through the list until we find the letter we want. That's A. Then we rip it out of this here, put it in the front. We wire this so that C still points to somewhere. And then if we read the list, it's A, X, Y, Z, B, C, and that's what the majority has voted for. Okay, so that's how move to front works. This time I'll start with the code here because I wanted to show how very, very similar encoding and decoding in this case is. We always start with the move to front list initialized with some order, and well, without any other options, just put the alphabet in sorted order. Then we start in the encoding. The code word starts empty. That's this epsilon here. Then we walk through each character in the source text. That's our character C. Then we find the position in our linked list, in the move to front list. So we walk from the front until we find it. That gives us a position P. That's the index, 0 based. That's what we store. And then we do the move to front step. For decoding, almost the same. We produce the source text, of course, not the coded text. We read one character from the coded text, and that's our position P. And we get the character by moving to position P in L. So in one you walk through the list and check what character you have, and the other you count down the index until you find position P. But in both cases, we do the same move to front step. All right. Let's see an example for that. Okay, I wanted to align this. That didn't work. Okay, let's see the example. So the first letter we encode is I. We find that in the list, it's at position 8 at this point. So that's our output. Now, before we move to the next letter, we rip it out here, put it in front. That looks like this. I is now here. Everything else shifted one position to the right. Next letter N, we walk through the list, find it at position 13. So that's the output. And then we put N in front of everything. There we are. That's our N. And everything else is shifted one position to the right. We do that again. E, we find it at position 6. That's our output. And we move E to the front. All right, we see how this goes. I think I can speed up the example. It's the same thing happening over and over. Now, I want to point out two things that might give you an intuition why this transformation is any good. if you look at these two Fs here, so now I wish I would have properly put this one off below the other, but you may just make out what happens. If I have twice the same character in the source text, or in general a run, that translates into zeros in the coded text because I'm putting it at the front and then using it right away again. And then there's other things like this weird pattern, 3 Cs. What would that correspond to in the source text? Well, it's the letters before this. That's this. If you look at these CIE, not so clear. Anything special about those? But if you look closer, it occurs earlier again. So a run like this occurs when there's a close repetition without reusing letters in between. But you can see there's some tendency, if the text has elements of boringness, then that can translate to zeros if it's a strict repetition. And a repetition of this kind might lead to runs of the same number. That's all I want you to take from this for now. So by itself doesn't help much. You have an alphabet of size sigma before, an alphabet of size sigma afterwards. But it turns out to turn things that we'll see after the next transformation into things that are easier to compress. Two comments about the output of this transformation are integers, so you still want to convert those to binary if you use it in compression. And of course, again, you have different options how to do that. The Elias code that we've seen in run length encoding has the nice feature that small numbers are represented with fewer bits. But of course, a Huffman code would always get you the best answer globally if you average out. One other thing I'd like you to think about is this deficiency of Huffman. I don't have this on the slide, unfortunately, but if you think about this text where I said, oh, it's very frustrating that Huffman codes don't seem to recognize that there's something to compress here. A bunch of A's and a bunch of C's. If you feed that through the move to front rule, you'll get some arbitrary letter, but then zeros. And then you get some arbitrary number and then zeros again. Now this is degenerate, of course, with all the zeros. You don't usually have that. But I want to point out that you have zeros and zeros. It didn't matter what the repetition is. So in a way, move to front manages to get different frequencies of characters down to the same numbers. Here we had lots of A's, here we had lots of C's, yet after move to front, they both correspond to lots of zeros. That's at least one step in the direction that might make a Huffman code after this more effective.